Okay, we are recording now. Okay, so again, you restrict the sine function to make it 1 to 1, so that's just the red line, so you can ignore whatever is drawn in black and just look at the red figure. So that means the domain is from negative pi over 2 to pi over 2, and that becomes the range of the inverse sine. Okay, so that means if x is a negative number, then the inverse sine of x is going to be an angle, and this angle is going to be here in quadrant 4. Then inverse sine of x is in quadrant 4. And then if x is a positive number, then the inverse sine of x is going to be in quadrant 1. Okay? That's what's important. Questions? Questions on this? Okay. All right. So same thing for the inverse tangent. Again, to understand the inverse tangent, we need to define the tangent, the restricted tangent function, because the original tangent is this one, and this is now 1 to 1. Okay. If I draw a horizontal line, it crosses a bunch of points. And in this case, because we have a bunch of pieces that are the same, the one that we take is the one that contains 0. So this is the restriction. Okay. So the restriction of the inverse tangent is once again from negative pi over 2 to pi over 2, the restriction of tangent, but this time we do not include the points because those are vertical asymptotes. Okay? So we have the inverse tangent function. So this function has range negative pi over 2 to pi over 2, but this time with parentheses. Okay? So once again, this is quadrant 4, quadrant 1. And if x is different than is less than 0, then the inverse tangent of x is going to be an angle in quadrant 4, like the negative version of it, like negative pi over 4, right? Something like that. And if x is positive, then the inverse tangent of x is going to be an angle in quadrant 1. So from 0 to pi over 2. So when I say this, let me specify this more. When I say this, I mean that inverse tangent of x, this is an angle, and it's between negative pi over 2 and 0. And here I mean, in quadrant 1 means it's greater than 0, but less than pi over 2. Okay? All right, so that's inverse tangent. And lastly, we're going to be looking at inverse secant again. So Franklin, do you have a question? Because you have your hand raised, that's why. So Adam, why do we have to have the red line going up only? So which one do you mean? Are you talking about tangent or are you talking about sine? So we are defining a piece of the function that makes it 1 to 1. Okay, so the whole sine function is now 1 to 1. So basically, what we want is a piece of the function that's 1 to 1. It has to be as big as possible. So and also we would like to be as close to 0 as we can. So that's the reason why we use 0. Then you move to the right, going up all the way up to x equals pi over 2. If you pass pi over 2, we go down and we lose the 1 to 1 property. Okay, so we stop there. But then we can also go back and get into quadrant 4. There is no need to avoid this piece right here. And that's why we take the piece down. So basically it's from negative pi over 2 to pi over 2. Okay? That's the restriction that we make. So now you can ignore the rest of the function, and that would be a perfectly 1 to 1 function. Okay, so as for sine, tangent, and then for secant, again, same idea. It's now 1 to 1. So what restriction do we make? Again, we want to have 0 whenever possible. So we're going to pick this one. So what we decide to do is we pick this one, and then we pick this one over here. Okay? Again, notice that I cannot get into this part right here because we lose the 1 to 1. We cannot get into this part right here because we lose the 1 to 1. Okay? So the restriction for the secant function to make it 1 to 1 is from 0 to pi over 2. And then from pi over 2 to pi, we need to skip pi over 2 because pi over 2 is a vertical asymptote. So that's quadrant 1, quadrant 2. Okay? So for sine tangent is quadrant 1 and 4. For secant is quadrant 1, quadrant 2. So y equals inverse secant of x makes sense now, and this has range from 0 to pi over 2 union pi over 2 to pi. Okay, and if let's see, so how do we do that? So if x is bigger than 1, because remember, the x for the inverse is the y for the original function. So what we're saying is, if x is bigger than 1, we're going to obtain an answer in quadrant 1. If x is bigger than 1, then inverse secant of x is in quadrant 1. And if x is less than -1, then the inverse secant of x is an angle in quadrant 2. Okay? And we can see that from the picture. When your x is less than -1, we're getting an angle in quadrant 2. Remember, x and y are switched. The x and y that we have in the picture are for secant. I'm talking about the inverse secant. So the x here is really the y, and the y here is really the x. Okay? Because it's switched. All right. So what you need to remember is this. So I quadrant 1, quadrant 2. So what you need to remember is that the range of the inverse secant is quadrant 1, quadrant 2. The range of the inverse tangent is quadrant 1, quadrant 4. And the range of the inverse sine is quadrant 1, quadrant 4. That's what you need to remember. Okay, so we're gonna need it. Okay, questions? All right, so we're gonna refer back to this whenever it's needed. So let me go back, and I'm going to revisit the last example that we did last time, but I'm gonna do it slightly different. It's the same, but without using the triangle, because I want to show you the two flavors, and then you pick whichever you prefer. Okay. So same example as last time. Let's say that we want to calculate the integral of dx over x squared, square root of 9 minus x squared. I'm purposely doing the same just to show you that, you know, that doesn't matter what option you decide to take. Anyway, you're going to get the same answer. Okay. Now here the reasoning is a little bit different. So we want to make a substitution, and my job is, what I want is to get rid of this radical. This radical is what's making this integral a little bit complicated. Okay. So how do I get rid of that? Well, if I can make the stuff inside something square, that square is going to cancel the square root. So try to think about what trigonometric identity do you know, so that when you plug that expression here in the x, it allows you to get something square. So you should think about sine squared plus cosine squared equals 1. So if you have 1 minus cosine squared or 1 minus sine squared, that's the other guy squared, right? The 1 squared is cosine squared. Do you understand what I'm saying? That's what we basically want to do. Now, this is not a 1, this is a 9. So you either factor out the 9, or you compensate by that by putting a 3 sign in here. If I put a 3 sign instead of in where x is, when you square it, you're going to get 9 sine squared. Then I can nicely factor out the 9. Okay? So you see this, and then, you know, this is something that you memorize, that when you see that expression, then the substitution that makes sense to do here is x equals 3 sine of theta. And it's pretty easy to see why. I already told you, because we want to take advantage of the Pythagorean identity of sine and cosine. And why the 3? Notice that 3 is the square root of whatever number comes in here. If you have a 7 here, then I will put here square root of 7. Okay? Just so that when I square it, I get the same number and I can factor it out. Okay, so when you do this, then dx becomes 3 cosine the theta. And there are some things that we should do. So for example, this tells me that sine of theta equals x over 3. Okay? So that means that theta is going to be the inverse sine of x over 3. In case of it shows up in our answer, you know that you need to replace theta by the inverse sine of x over 3. And then remember that this is now an angle. So this is in quadrant 1 or quadrant 4. For this integral, it's not really relevant because this is an indefinite integral. But this is important if you have limits of integration. If you have limits of integration, you need to know whether your x is positive or negative, because depending on the sign of x, that will be the quadrant that you are, okay? And that will matter in the substitutions that you will make. Okay, so we have this. Now we already have, because x equals 3 sine, we already know what x squared is. Let's work with the radical. It's better to simplify the radical down here. So we have the square root of 9 minus x squared is going to be equal to 9 minus, I'm going to replace now what we have. That's 3 sine of theta squared. And let's simplify, okay? So that's 9 minus 9 sine squared, factor out 9. So the 9 comes out as a 3. And then 1 minus sine squared becomes cosine squared. And then this becomes 3. What do we write? Should I write cosine? So technically we need to write absolute value of cosine. Because remember, if you do absolute value of a square root of a squared, this is not a, this is absolute value of a. Because you have to make sure that your answer is always positive. Okay? So that's why here is very important to analyze what's going on here. So what do we know about cosine of theta? Well, it really depends on theta. If theta is in quadrant 1, this is a positive quantity. If theta is in quadrant 2, because those are the only two choices, what do we know about cosine in quadrant 4? Sorry? It's positive. Remember, cosine is positive in quadrant 1, quadrant 4, because that's the x. Cosine is negative in quadrant 2, quadrant 3. So the only possibilities for theta, according to the substitution, are quadrant 1 or quadrant 4, and in both quadrants, the cosine is always positive. So we are free to remove the absolute value, okay? Since cosine is positive. Once again, this is something that you memorize if you want to go this route. You don't have to do this analysis every single time. If you don't memorize it, then you need to analyze it every single time. Okay? But then I'm going to give you the rules, the formulas, if you will. Anyways, the point is that regardless of the quadrant for theta, we have two choices only, 1 or 4, because theta is an inverse sine function, and we know that the range of the inverse sine is quadrant 1 and 4. In any of the two, the cosine of theta is always positive, so that's why I can get rid of the absolute value. Okay? All right, so that means our square root equals 3 cosine. So the square root of 9 minus x squared equals 3 cosine. And once we have done this, then we are ready to evaluate. So the integral that we wanted to compute, now with this substitution becomes, so what do we have for dx? Dx is 3 cosine of theta. So we have that here, okay? Over, now what's x squared? That's 9 sine squared. And then the radical is 3 cosine. I'm just replacing whatever we have and just replacing each term, okay? So the x is this guy. That's all I did. I replaced it there. Then x squared is this x squared, right? So that's 9 sine squared. And the square root, we already have it here. So all I did was put everything in my integral. Do you understand this? So now instead of x, we have theta. So this is now a trigonometric integral. So we already computed this last time. So let's just do it quickly. So we get 1 over 9. So we have 1 over sine squared, which becomes cosecant squared. And cosecant squared, the integral of cosecant squared is negative cotangent, right? So this equals negative cotangent over 9. So negative 1 over 9 times cotangent of theta. Now, of course, our variable is not theta, our variable is x. So what we need to do is we need to go back to x. How do we do that? Well, you either use identities from here. For example, you know that sine of x equals x over 3, and you may, and remember, with this information, you can find the remaining 5 trigonometric functions, okay? And how do you do that? You use this information to draw a triangle. So the point is that there is no escape from the triangle anyways. You either draw it at the beginning to allow you to do this The good thing about the triangle is that it tells you what substitution to make, and you avoid this algebra part. Because the triangle itself will tell you what the radical will be equal to, as it did to us last time. Okay? But if you don't want to do the triangle, that's fine. You can do it purely algebraically like this. But at the end, when you need to go back to x, how do you do it? You only know that sine is x over 3, but now we need to figure out what cotangent is. Okay? And the way you do that is you use this information to build your triangle. Okay? And remember, sine is opposite over hypotenuse. So that means, actually, I'm going to do it up here. So notice, remember, even though you're going to look at this triangle above, when you look at the notes, remember this triangle was drawn last using this idea. Okay? If theta is here and sine is x over 3, that means this is an x and this is a 3. Right? Using Pythagorean theorem, this side will be 9, square root of 9 minus x squared. Do you understand this? And we are after cotangent, so now you look at the triangle and write down what cotangent is. What's cotangent? Tangent is opposite over adjacent, so cotangent is adjacent over opposite. So this would be negative 1 over 9 times square root of 9 minus x squared over x. Okay? Cotangent is adjacent over opposite. All right, questions? Do you understand this? So I'm gonna be honest, I don't like to do this. I feel it's too long and there's no reason to do that. Anyways, you have to draw a triangle. So what I prefer to do is, at the moment that I see a problem, I use the problem to draw my triangle, and the triangle tells you what to do after that. You just need to understand how to read the triangle, which is what I'm going to explain.
How did you get the 3 sine theta from the triangle?
No, the triangle was the last thing that I drew. So it was not from the triangle. I said it out loud. It was thinking about an identity. The thought process is you want to get rid of this square root. So that means I want this to be something squared. So what do you know from trigonometry? That when you have something minus something, it becomes a quantity squared. You should think about 1 minus sine squared. 1 minus sine squared equals cosine squared. So that's what I want. I want to have a 1 minus sine squared in here. And I can make it so if I let x be 3 sine. Why 3 and not just sine? Because if I put sine, then I have 9 minus sine squared. I don't have 1 minus sine squared. So you put the 3, so the 9 comes up, and you can factor. And then the 1 minus sine squared pops up. So basically, the number that you put here is the square root of whatever number you have here at the beginning. Okay? And then you learn that every time that you have an expression like this, that's a substitution that you make. Now, I want you to understand that here you have a choice. You could also have written 3 cosine, okay, and it will also work. You will get a different integral at the end, but at the end of the day, once you finish with your answer and you go back to x, you will get the same answer that we got. Just that your triangle will be different, because here, instead of putting x on this side, you could put it here. Okay, 3 is definitely the hypotenuse, but x could be the adjacent instead of the opposite. Putting the x in the adjacent makes you the substitution x equals 3 cosine. Okay, but it will be a similar process. Yes, you have a question.
Yeah. Why is it in quadrant 1 and 4? If we got the first problem we did sine, isn't it from 3 and 1?
No, that's what we just did.
For sine.
Yes. Inverse sine function. This is quadrant 4, and this is quadrant 1. So when you define the inverse sine
question, okay.
The range is quadrant 4, quadrant 1. So I said this is what you need to remember, but the inverse functions. That's important.
But that's for the inverse function, not for the actual sine function.
No, for the inverse function. That's what we're dealing with. We're dealing with the inverse function because when you make the substitution, you want to know what this theta is. You see, remember, our original variable is x or t or whatever the variable is that the problem gives you. But we're going from that variable to theta. You need to know this theta is an angle, but where is it? Because we're using a trigonometric function to define it. Then if I say that sine of theta is x over 3, that means that theta is going to be the inverse sine of this quantity, right? And that means then that it has to be in quadrant 1 or 4 because that's where this is defined. Now, like I said, this is not too relevant for this integral because it's indefinite, but this is very relevant when you have signs, when you have limits of integration here. Because then it will tell you whether the numbers are positive or negative, then that means that this would be either in quadrant 1 or 4, one of the two. And that may then change some substitutions that you're going to make along the way. We're going to do some examples that you're going to see that. When it's indefinite, it's not really too relevant to worry about this. Like I didn't even mention it last time. When we're doing it, I didn't even get into it. It was not needed. But it's good practice. Every time that you make a substitution, you need to know this new variable that you are introducing, what is it? I know it's an angle, but where is this angle? That's a natural question to ask. Where is theta? Well, 1 and 1/4. Okay? All right. Jason, you have a question?
Professor, we can't solve this problem with U substitution? Or you're just doing another way?
So what U substitution would you make?
Yeah, that's a good point. I mean,
we did a substitution, right? We did a substitution. It's called trigonometric substitution. But another substitution, which one would you make?
Trying to substitute for x, same way we did in section 2, I guess.
Okay, wait. You may want to, let's see. Say that again. See if I can hear you better.
Yeah, substituting for x. When you take out the 9 and you get x,
yeah, but x equals what?
Squared.
X equals what?
I don't know. I mean, yeah.
Well, that's the point. That many times, it's not. I mean, if instead of an x squared in the denominator, we had understand that if the integral would have been like this, right? You're free to go through all of this, but you shouldn't. You can just make a super easy U substitution. U equals 9 minus x squared, and then the du is right on top, and everything works nicely, right? Something like that, you do it with a simple U substitution. But, the moment that, for example, also if the x is not here, if it's like this, you can do it like this, or using the ideas that we did at the beginning of the semester. This is an inverse sine function, right? When you do this integral, this is going to be an inverse sine. You factor the 9 and all of that business. But when you have this x squared in here, then it kind of make any other substitution. Maybe it works, but it will be either more complicated or you have to think a little bit more. Okay?
Okay.
So again, I'm not saying this is definite that you have to do this. There are situations in which you could do something else. But those are on a case-by-case basis. Okay? But this always works for this type of integral. Okay? Again, remember, all I'm doing is I'm giving you tools. At the end of the day, you have an integral, you decide how you want to solve it. With all the knowledge that you have, you pick the tool that you feel is the one that the easiest to solve the problem. Okay? There are always multiple ways of going about it. I'm just giving you the tools. All right, so there are basically now 3 types. So let me introduce that to you, and then like I said, this is what I like. So I'm gonna be sticking to the triangle approach, okay? Instead of memorizing that. But anyways, I'm gonna give you the formula for this. Basically, when you see something like this, you will say, oh, substitution is 3 cosine. You want to memorize that? 3 sine. You want to memorize it? Fine, okay? But I'd rather do the triangle. All right, so let me explain this. So idea. The above process can be done with integrals that contain the following expression. That contain the expressions. Now, there are 3 main cases, okay? So the one that we just saw, I'm gonna write it here in general. So I'm gonna write a squared minus x squared. And when I write x squared, just think of it, maybe you don't have a perfect square, but just whatever number you have, you can always write it as a square root squared, okay? It's just that I want you to focus on the number a. It will look like this, or, so a number minus x squared, that's what I mean by this. Or x squared minus a number, okay? Or x squared plus a number. That's what I want you to. So when I write a square, I really mean a number, okay? But I want you to look at it as something squared. So if you have, for example, x squared plus 7, just think of this as being x squared plus square root 7 squared, okay? So that this discussion can make sense to you. All right, and what I want you to realize is that every time that we see an expression like this, you can think of Pythagorean theorem. So with this expression, you are able to draw a triangle. In other words, these two numbers or these two quantities that are in the expression, they represent two sides of the triangle, and then the whole radical will be the third side. You just need to figure out which one is it. Now, let me remind you of Pythagorean theorem. What does Pythagorean theorem says? Let me put this down here. So recall Pythagorean theorem. So if you have a right triangle, okay, this is a 90-degree angle. Now I don't want to write A because we already have A, so I'm gonna write what do I write? Okay, I'm gonna write. Okay, I'm gonna put A, but please understand that the A that I'm putting here is not the same as the A that is below in the formula. Do you understand this? Okay, so if you have a right triangle with sides A, B, C, what does Pythagorean theorem says? So then A squared plus B squared equals C squared. Everybody okay with this? How else you can write this? What else can we write here? We can also say that A squared equals C squared minus B squared, right? But we can also say that B squared equals C squared minus A squared. Does that make sense? So, moral of the story. Notice that here, what are A and B? Those are the legs of the triangle. So, this is a leg, this is a leg, and this one here is the hypotenuse, right? So what that means is that every time that you see, for example, this expression, what are the numbers that we have in there? So when you are adding two numbers, what do they represent? They represent the legs of your triangle. And then the square root of that is the hypotenuse. Because if I take square root of C, so if you will, so C equals the square root of A squared plus B squared. Then A is the square root C squared minus B squared, and B is the square root C squared minus A squared. Yes? In other words, every time that you see this radical on top, that means that radical represents the hypotenuse of the triangle, and the two numbers that you see are the legs. And the square root of the number are the legs. Yes? When you see a radical like something minus something, right? Something squared minus something, that the number in front, you know, the first number that appears square, that represents the hypotenuse. The one that's negative, that's one of the legs, and the radical is another leg. And similarly with the other. Yes? So with that in mind, now you can easily see what's going on here. For example, let's take a look at the red triangle. What's the hypotenuse of this red triangle? What's the hypotenuse? No. Look at the radical. Tell me a letter. A. Okay, you didn't understand. Let's back up.
Oh wait, no. Okay, no, I get what you mean.
Okay, but let me repeat. Okay. Look at this. So the red triangle has this form, right? It's coming because of this form, right? The stuff in front, what is it? What's the letter of the stuff in front? Inside the radical, the first term. What's the letter? C. What does C represent in a triangle? The hypotenuse. So every time that you have something, the square root of something squared minus something, the first guy is your hypotenuse. The other guy is your leg, and then the whole radical is the other leg. That's what I'm trying to say here. Do you understand this? So if you look at this red expression, what's A? The hypotenuse. What is X? One of the legs. Here is when you make a choice. Which one do you want? Typically, we do this because, you know, typically our theta is here. So our substitution would be sine because it's opposite or adjacent. But if you put the leg on the other side, then that would be a cosine substitution instead of a sine substitution. Okay. And then what's the other side? It would be the whole radical. Do you understand how we build the triangle? So let's see. The blue triangle. Tell me, what's the hypotenuse? Good. So the blue triangle, the hypotenuse is x. And then one of the leg is A. So here, typically, we put it here. So I will use, this is the one that will give me secant. Okay? Then I'll tell you how. Okay? And then the other side is my radical. And then lastly, for the black triangle, what's the hypotenuse? Very good. The radical, right? The hypotenuse is the radical. Therefore, what we see in there are the legs of the triangle, right? So typically we put x here and a here so that we have a tangent substitution, opposite over adjacent. If you switch them, you can switch them, but then you will have a cotangent substitution instead. Okay? It depends on your taste. And then this is my hypotenuse. Did you understand how to build the triangle from that expression? Because that's it. Once you have this, the triangle tells you everything else. For example, what would be the substitution in the red case, which is basically the example that we did above, right? The red case, here is what you have to think about. Remember, you want to go from x to theta. So, and you don't want to involve the radical expression. So how do you use the side, the side of the triangle with x and the side with the number? What's the number here? The number is a. There is always a side that has a number. Okay? It could be the hypotenuse or it could be one of the legs. Okay? It depends. So how do you relate in the red case the x and the a with theta? So just say out loud the name of the sides and the function will come to your mind. What side is this relative to theta? Opposite. And what's a? Hypotenuse. When you say those two names, I hope that the word sine comes to your mind. Yes? Yes? Opposite, hypotenuse, you should be thinking about sine. You could think about cosecant, but almost nobody thinks about cosecant, right? So here you will say, well, look, sine of theta is x over a. So that means x is a times sine. Did you understand this? Now, of course, if you don't like a triangle, you can just memorize. Ignore the triangle now. Memorize that every time that you have this form of the radical, this is the substitution that you make, which is the approach that I talked about. Okay? You can. But then, if you don't use the triangle, then you have to go ahead and plug in and do the algebra to see what the radical is. But here, the triangle tells you what's the radical, anyways. Okay, so that's a substitution for that case. How about the blue case? Let's see. What are the sides that we should be considering? Adjacent and hypotenuse. What function comes to your mind when we say this? Cosine. So that's fine. So let's put cosine. So cosine is adjacent over hypotenuse. Yes? Remember, you want to avoid the side with the square root. You need to use the other two sides. So now, solving for x, what do we get? We get that x is a over cosine, but we don't like to work with fractions. So what's 1 over cosine? A secant, right? So in this case, the substitution is a times secant of theta. Is this clear? All right, and then let's see, for the last one, what are the sides that we should worry about? Opposite and adjacent. What comes to mind when we say these words? Tangent. So of course, this requires that you need to know what these functions are, right? Sine, cosine, tangent, and so on. How they are defined using a triangle. So tangent of theta is x over a. So x is a times tangent. Are we okay with this? All right. So, okay, so we have this. Now, one more little detail. Then, of course, to replace the radical, then you can use a triangle to replace the radical. For example, actually, let's write it down. What function would you use? Now you don't want to use the side with the x. Remember, you always use the number, the side with the number, to make your substitutions. Now let's find a substitution for the radical. Let's go back to the red. What function should we use for the radical? Say the name of the side. Adjacent, hypotenuse. What comes to mind? Adjacent, hypotenuse. What comes to mind? Cosine. So cosine of theta is adjacent over hypotenuse. So Now you get here for free that your radical is 8 times cosine. Do you understand this? And that way you avoid doing all of this business that we did. Okay? Let's go to a blue. Remember, now we're solving for the radical. Always use the side with the number to help you. So what are the sides that we're interested in? Always use the number. We want to solve for the radical. What is it? Opposite and adjacent. What comes to mind? What comes to mind? Opposite, adjacent, tangent. You have to focus here. I mean, this requires you to, to be careful. It's not supposed to be hard, but you have to be careful. So tangent. So
in that triangle, it doesn't matter if we change the square root to the other line.
Then instead of tangent, you will need to deal with cotangent. You will have a cotangent in your integral. You see, if the square root was, first of all, if it was on the other side, here your substitution will be with a cosecant. And then this will be a cotangent. So when you plug into your integral, when you make the substitution, you will be dealing with cotangent instead. That's fine. Doesn't matter. Okay? All right. I'm going to come back and say a few words about this, but let's finish with the other one. How about the radical? In the black triangle. What are the sides involved for the radical? Adjacent and hypotenuse. What function comes to mind? What comes to mind? Either cosine or secant, whichever you want. What do you want to say? Cosine or secant? Don't be afraid, whichever.
Nobody likes cosine.
So cosine, unfortunately, secant is going to come up because the radical is in the denominator, right? So when you solve for it, the secant will pop up. But let's say that you want to go with cosine first, then the secant will make its entrance anyways. So adjacent over hypotenuse. Okay, then solving for the radical, we get a over cosine, which is a times secant. Okay. Let me explain to you. Let's say that you wanted to avoid the triangle and you wanted to do it algebraically. Why the substitutions are the way they are? Look, when I put inside my square root, let's look at the red. If I take this a sine and I put it in here, the point is that a 1 minus sine square will pop up. You get cosine squared. You simplify, and the cosine comes out in the radical. That's why you have this cosine showing up in here. Yes. Now, what happens if I put secant? A times secant in here. What's going to happen? Sorry. In here. What's going to happen? You factor out your a squared and you will end up with a secant squared minus 1. What's secant squared minus 1? Tangent squared that you cancel, and that's why you get a tangent in here. Right? And then if I were to plug in a times tangent in here, oops, keep highlighting the wrong stuff. I put it in here. Then the a squared factor out, and we end up with tangent squared minus 1, plus 1. What's tangent squared plus 1? Secant squared. Cancels with the radical, and you get your secant. Right? So that's really, but the point is the triangle is telling us all of this, and we don't have to worry about those identities, okay? But if you like using the identities, you can, and you can avoid the triangle. That's why I wanted to show you this. You can do it. Look, we did the triangle at the end. Okay, we actually solved the whole thing without looking at the triangle, so it's possible to do it like that. Okay, but what I want you to understand is that all this stuff that I draw came from the picture. You don't have to memorize this. You just need to know how to build the triangle. Triangle tells you everything else. You need to know what to look at, of course, but it tells you all the formulas to write. You okay with this? Now, one more piece of information before we start doing examples. Let's see here. So let's check for consistency. Imagine that, that we care about the intervals and then whether x is positive or negative. Adam, do you have a question?
Yes. How did you decide what sides to label a and x in the triangles?
You have a choice. So, okay, hold on. No, it really depends. Did you understand what I said about the Pythagorean theorem?
Yeah, I believe so.
So just in case, look at what is highlighted here on the right part of the triangle. This means that whenever you have a radical of this form, something squared minus something squared inside the radical, the stuff inside, which is this C, that corresponds to the hypotenuse of the triangle. And the other one is one of the legs. And then the whole radical is the other leg, because A is a leg and B is a leg. Do you understand this?
Yes, I think so.
Okay, so in my red triangle, it has that form. So that means that the first number that shows up, which is the A squared, the A is my hypotenuse, and then the other guy is one of the legs. Here you have a choice. You can put it the leg that I chose or the other one. That will make a difference in whether the substitution is a sine or a cosine substitution. It doesn't matter. It's just that I like to stick with the same substitution all the time. Otherwise, we're interchanging and so on. So I prefer to put it in the opposite. If you like adjacent, by all means, you can do it. Okay? It has to be consistent with everything else that you write after that. And the same thing for the other two. The position of what's happening inside the radical tells you which one is the hypotenuse and which one is one of the legs. Did you understand this?
Yes.
Okay, good. All right, so last piece of information is, let's check for consistency here. And here is what I mean.
Professor, for the second one,
Uh-huh.
could you write it the same way as you did for the first and just use sine? Or were you just using that to show us those?
No, because notice that the blue one is different. The X
Oh,
is the hypotenuse. In the first one, the X is one of the legs. And in the blue one, the X is the hypotenuse. So it's different. It's a different situation. A number minus X squared or X squared minus a number. Those are two different things. Yeah. All right. So in here, again, remember I gave you a whole discussion about the angle, right? So this means that theta equals the inverse sine of x over a, right? Because we have the substitution, the sine is x over a, so that means that theta is going to be the inverse sine. So theta is going to be in quadrant 1 or 4. So we need to make sure that what we wrote here in the last line with the radical is consistent, because why am I saying that we have to be careful? Because this radical is always positive. Square root of something is always positive, right? And cosine could be positive or negative. So we have to make sure that what we're writing here makes sense. Well, in this case, it's consistent because both in quadrant 1 or 4, our cosine is positive, so we don't have to do anything. Okay? Let's take a look at the next one, the blue case. So so theta is going to be what? So we have the secant is x over a, so that means that theta in the blue case equals the inverse secant of x over a. Now, we know that the range of inverse secant is either quadrant 1 or quadrant 2. That was a little discussion that we had before. So this is either in quadrant 1 or quadrant 2. Now we have a problem, because our radical is defined in terms of tangent. In quadrant 1, tangent is positive. That's good. But when the angle is in quadrant 2, what do you know about tangent in quadrant 2? That's negative. But we're saying then the square root equals something negative. That makes no sense. Understand this? So what do we do in that case? You have to manually put a minus in here. So there are two formulas for this case, and it comes because of this. So I need to stick an absolute value here, because this term could be positive or negative, okay, depending on the quadrant. So to remove the absolute value, you have to look at the problem and then make a decision. So if theta is in quadrant 1, okay, then this guy equals a times tangent. But then if theta is in quadrant 2, then this radical is going to be, so we put a times tangent, but you need to understand that theta is in quadrant 2, so tangent is negative. How do we make it positive? We have to manually put a minus. Do you understand where this minus is coming from? Because we are in the situation in which our angle is in quadrant 2, which gives us a negative tangent. We have to make it positive. How? By putting a minus. Because remember, really, what happens is that you have here an absolute value. Okay? It's just that, for example, in the first case, we can ignore the absolute value because the cosine is positive all the time. But here, you cannot just ignore it. Because this could be both positive or negative because of the quadrants. Okay? So that's the case that you have to be careful about, because the other one is also fine. Let me just write it so you see. So in this one, our theta is the inverse tangent of x over a, and the range of inverse tangent is quadrant 1, quadrant 4. And in quadrant 1, quadrant 4, secant is positive. So this square root will always be positive, and we're safe. So the only case that you have to be a little bit careful is the blue case. Okay? The blue case is the one that's slightly dangerous.
No, the other way. Down.
Okay? So that's everything. So now, with the time that we have left, let's do examples. But basically, with this, you can do now any exercise that comes your way. Well, this combined with the previous section, because remember, all this does is it takes that integral and turns it into a trigonometric integral. Then you have to apply all the techniques that we discussed earlier, okay, last week, last class and the previous week. All right, and then remember to go back to theta, to go back to x. Once you finish solving the integral, to go back to x, you rely on the triangle, okay? All right, so let's do examples so you can see this in action. So let's do, so evaluate the integrals.
Inverse tangent is on quadrants
1 and 4. It's there, so you can see that later. We did, that's why I did the summary at the beginning, because that was important. Again, you really need to be super concerned about that when your integral is definite. If you see limits of integration, then you have to be very concerned about it. But let's see, let's do one without limits first, and then we do one with limits. Okay, so let's do the integral of x squared over square root 4x squared plus 1. Again, always be mindful of the integral that you get, because you may be able to solve it with a little substitution. For example, if I didn't have the square here, this would be very easy, right? Just let u equals 4x squared plus 1, and then you're good to go. But by putting a square here, it changes the game completely. Okay, so let's do this. So again, I see this, and I immediately think about Pythagorean theorem, right? Okay, so let's draw a triangle. So what do we see? Do we see the hypotenuse inside the radical, or those are the legs? What do we see inside the radical? The legs. So one of the legs is what? 2x. You have to take square root. Remember the formulas, it was everything squared. So one of the legs is 2x, and the other one is a 1. Do you understand this? Why 2 and not 4? Okay, and then the hypotenuse then is my horn. Anyways, you use Pythagorean theorem to get the other side, you have to get the radical. If you would have written a 4 here, when you do Pythagorean theorem, you will get 16, and then you realize that something went wrong, because we don't have 16 in the problem. Okay? So even if you make a mistake here, always do Pythagorean theorem to compute the other side, and it has to match what you have in the integral. If it doesn't match, that means that you put something wrong in the triangle. So that's a good checking point that you can use. Okay, the moment that we have the triangle written down, then everything else starts to follow. Let's see, what function should I use? Remember, use the side with the number. Now we want a substitution for x. So you need to use the side that has x and the number. So what function should I use? Tangent. So try not to look at the list that we have from before. Just think about it. So you learn it. So tangent is opposite over adjacent. So that's 2x over 1. So that means that x equals 1/2 tangent. Yes? Okay. So the moment that you have the x, we immediately can figure out, the moment that you have x, we can figure out dx. How? By taking derivative. So what's the derivative of tangent? Secant squared. So 1/2 secant squared. Okay? And before I move on, let's make it a habit to always writing down what theta is. So tangent of theta is equal to 2x. So that tells me that x is gonna be, theta is gonna be inverse tangent of 2x. Okay. Whether we need that or not, we will see. In this case, we may not need it, but it's good to have it there. Okay, so I already now always look at your integral. We have a substitution for dx. We have a substitution for x. We just need now a substitution for the radical, right? Let's go back to the triangle. What function should I use for the radical? Remember, always use the side with the number and then the other side that you want. So adjacent, hypotenuse. What function do we use? Cosine. Here the choices are either cosine or secant. Okay, secant you will get it right away, but if you use cosine, you solve and then eventually the secant will pop up. So as adjacent over hypotenuse. Now here is an interesting trick. You can solve for the radical, right, and get a secant, and you will have a secant in the bottom. But if you think about it, we really have a 1 over the radical in the expression. And that's cosine. So you can just put cosine and then that's it, right? So there is no need to write secant. But I'm going to write the secant just to stay, you know, because what I'm saying is that then this right here already contains is x squared times 1 over this. Right? So you could just rewrite this, replace this by a cosine, and that's it. Because that's what we got. Okay? But it's okay, I'm just going to put secant. So this is secant 1 over cosine, which is secant. Okay, so now we have a substitution for every single thing in the integral. We go to the integral and plug in. All right, so x is 1/2 tangent, so x squared is going to be 1/4 tangent squared. Yes? My radical is secant, and my dx is 1/2 secant squared d theta. Questions? What we have so far? No? So now we have an integral, that's a trigonometric integral. Let's simplify and let's see what's the actual integral that we get, and then we solve it. So let's see, this 1 over a is going to come out from here. And then this secant cancel with this secant here. So we get the integral of tangent squared times secant d theta. How do we solve this integral? I think this was a painful case, the last one. This is the one that we need to turn tangent squared into secant, distribute, and then we get secant to an odd power, and we have to do integration by parts. That's
Unlucky.
You know, that's that case. That was the last one that we discussed last time. So we turn tangent squared into secant squared minus 1. Distribute the secant, we get a secant cube and a secant. We know what to do with secant cube by parts, and secant we know what's the integral of secant. Okay, so I'm gonna do that now. All right, so this becomes secant squared minus 1 times secant, distribute, and so we get secant cube minus secant d theta. Okay, so I'm gonna go ahead. I mean, we did okay, but I'm not gonna cheat. I was gonna go back to 2 lectures, the previous lecture, and grab the answer from there, but let's do it. So I'm gonna integrate secant here, okay? So let's say I'm gonna call it the integral secant cube. So remember, the idea is that we write this as secant times secant squared, because secant squared is easy to integrate. So we let u equal secant, and then dv is a secant squared d theta. So du is secant tangent, and v is tangent. So this is going to be uv, so secant tangent, minus the integral v du. So that would be secant tangent square. And then the idea here was to rewrite, because now this is similar to, now we rewrite this as secant square minus 1. So this now becomes secant cube minus secant. So the integral with secant cube is negative, so I'm going to move it to the other side positive. So we're going to get 2 secant cube is going to be equal to secant tangent. And then when you distribute the negatives, that gives me a plus the integral secant. Now, instead of computing the integral secant, notice that then we need to subtract. There is another integral secant that we need to subtract, so I'm going to do that at the end, okay? So moral of the story, secant cube equals 1/2 secant tangent plus 1/2 integral secant. I'm going to put that up here. So this now becomes 1/8 times, so the integral secant cube is this, 1/2 secant tangent plus 1/2 integral secant, but then we need to subtract another integral secant. So this one that I'm subtracting is this one right here, okay? The first one that I have is from our work below of secant cube, but this other one was there. So I'm going to combine these two, that gives me -1/2. I'm going to distribute the 1/8. So we get 1/16 secant tangent plus minus 1/16 the integral secant. And what's the integral secant? ln secant plus tangent. Okay. Now we need to go back to x, but before I go back to x, questions up to here. Again, starting from this line is the previous section. Okay. Any questions?
I have a question.
You okay with this? So did you understand how to make the substitution? In other words, do you understand how to get to this integral from the original? That's the new stuff. The rest is what we did earlier from before. Okay. All right. So now what we need to do is go back to x. How do we go back to x? Let's go to our triangle. Now we're going back to x. So this is 1/16 times, what do we need? Secant of theta. Let's go to a triangle. What's secant? Hypotenuse over adjacent. So secant is the square root, right? Square root of 4x squared plus 1. Times tangent. What is tangent? Opposite over adjacent. So tangent is 2x. Minus 1/16 ln of square root of 4x squared plus 1 plus 2x. And if you want, then you can simplify and then write it a little bit nicer. Simplify the 2 with the 16 and so on. So then this becomes x square root of 4x squared plus 1 over 8 minus ln square root of 4x squared plus 1 plus 2x over 16 plus 6. All right, questions? You seem to be in shock, but I want you to understand that if you know how to get to the highlighted integral, then the rest is from the previous section. So that means that you just need to review the techniques that we discussed earlier. Okay? The new stuff that I'm trying to teach you now is how to get to the highlighted integral. Because The rest is from before.
Could you go down?
Okay. So remember, the technique there was to turn tangent square into secant square minus 1. Distribute the secant, you get odd powers. And how do you deal with secant to an odd power? By parts. That's the idea. Okay? You can look at this carefully later. Because I know several things happening there. It's just that I want to do another example. Otherwise, we take the whole time doing one example. Any questions on this? No? Okay, so let's do one with limits of integration. Okay? Let's do one with limits of integration. Let's see, I call this one A. So let's do B. Let's see, integral of from square root of 3 to 2 of square root of x squared minus 3 over x. Let's see, I'm gonna take attendance. Try this on your own. Let's see how far you can get. And then we do it together. So I'm gonna take attendance. Those of you that are on Blackboard, remember to type here in the chat, okay? So again, the first thing is that it's obvious that because we're in this section that the substitution that you should do is trigonometric sub. But remember, later on you will have integrals that you need to make a decision. Do you understand by looking at this that a trigonometric substitution is in order for this problem?
Yes.
Again, you see that radical with that expression, you need to think about trig sub. Always try to see if there is an easier substitution that will do the job, okay? But if you don't see it right away, trig sub is the way to go whenever you see a radical like that. All right, so let's make a triangle. Tell me, what do we see there? So x, where does it go? Very good. And then, what do I write?
Then square root of 3
Good. Where?
in the bottom left.
In one of the legs, and I'm gonna put it in the bottom. Okay, so we use secant. If you put it in the opposite, you will need to use cosecant. Nothing wrong with it, but then you have to deal with that. Okay, I prefer to take derivative of secant than derivative of cosecant. That's just why I'm doing this. Okay, questions? And then when you use Pythagorean theorem, remember, just do it so you can check. Is x squared minus the other leg square, which is a 3, and that coincides with a radical, so we know that we didn't make a mistake. Okay. All right. So for the substitution, we're gonna use adjacent over hypotenuse, so that means cosine of theta. So x is gonna be square root of 3 times secant. Okay. So from here immediately, this tells me. So you can either use the inverse secant or the inverse cosine. It doesn't really matter which one you want. But since we talk about secant, then let me talk about secant. But the range of the inverse secant and the range of the inverse cosine, they are exactly the same. It's quadrant 1, quadrant 2, because they are basically they're related to each other. Secant is 1 over cosine. I'm saying that because you could say, oh, then here theta is inverse cosine of square root of 3 over x. Okay. If you want to do it from this point of view, that would be inverse secant of x over square root of 3. You have to flip this. It doesn't matter, it's the same thing. What's important is the fact that this is in quadrant 1 or quadrant 2. Okay? Now I want you to tell me where is it. Because we know who is x. What do we know about x? X is between square root of 3 and 2, right? So x is positive. So when x is positive, you're doing the inverse cosine of something positive. The inverse cosine of something positive is in quadrant 1. If you do the inverse cosine of something negative, it's in quadrant 2. Do you understand this? So here, this really matters. So this actually in quadrant 1, since square root of 3 over x is positive. Okay? You have to make this decision, this distinction, every time that you have a definite integral and you make this type of substitution. Okay? Again, the same thing would have been if you had the inverse secant. Okay? Exactly the same thing. Okay, so now we move along. So that means that dx is going to be square root of 3 secant tangent d theta. We also need a substitution for the square root. So square root of, okay, so I'm gonna use tangent, right? So tangent of theta equals square root of x squared minus 3 over square root of 3. Now, at this point, you need to make a decision to see if this is consistent, because we're basically saying that this square root equals square root of 3 times tangent. So here we need to see our angle is in quadrant 1, therefore tangent is positive, the square root is positive, we are good. If the limits would have been from -2 to negative square root of 3, for example, the angle would be here in quadrant 2, and therefore we need to put a minus in here. Do you understand what I'm saying? Tangent is positive in quadrant 1 and is negative in quadrant 2. Look what we have on the left hand side. The square root of something equals this quantity. Square root is always positive. Okay? So if this has the possibility of being negative, we need to be careful. And the quadrant tells you, because we know that we are in quadrant 1, we are good. But if my limits would have been from -2 to negative square root of 3, for example, which is the next example that I wanted to do. If my limits were negative, that means x is negative. If x is negative, the stuff that I'm doing, the inverse cosine here is negative. That's going to give me an angle in quadrant 2. Okay? Making tangent negative. And so we need to make it, we need to force this to be positive for this to make sense, so you have to put a minus. That was the tricky case that I was discussing here. That's a blue case. You see how in the blue case, we actually split it into situations. Depending on the quadrant that the angle is, that's the substitution that you make. If it's in quadrant 1, it's just a times tangent, the radical, but if it's in quadrant 2, you have to put the minus. Okay? So just be mindful of that. All right, so just finish it because we are running out of time. Okay, so I have this. Now let me go back and start making a substitution. So the radical is square root of 3 tangent theta. X is square root of 3 secant theta. Dx is square root of 3 secant tangent d theta. And also we change the limits. I'm just throwing in what I have in here. I'm not doing anything weird. Just throwing in what I have in here. Now let's change the limits. Let's see. When x equals square root of 3, I'm putting the square root of 3 here, so I get cosine of theta equals 1. What angle do you know whose cosine is 1?
0.
That's 0. Because remember, it has to be between quadrant 1 and quadrant 2. Okay? And then when x equals 2, I have here square root of 3 over 2. What angle do you know whose cosine is square root of 3 over 2? That's 30 degrees. It's pi over 6. Remember, you need to know this. You need to know pi over 6, pi over 3, pi over 4, and all the quadrantals. You need to know sine, cosine, tangent, all of those values. Okay? If you don't, then put the inverse cosine and use a calculator. But then that would take you more time. Okay? Adam, you have a question?
How did you, what trig function did you use to plug in square root of 3 and 2 to find the new limits of integration?
Okay, can you talk a little bit louder? I cannot hear you.
What trig function did you plug square root of 3 and 2 into to get the new limits of integration?
In here. Because I prefer to think in terms of cosine for this kind of stuff. I mean, typically I don't remember at the top of my head the value for secant. I first think about cosine and then I flip it to get the secant. So I plug it in the cosine one. So x equals square root of 3, you get a 1 in here. So what angle has cosine equals to 1? That's 0. Right? And then if we put 2 in x, then that's square root of 3 over 2. What angle has square root of 3 over 2? That's pi over 6. Because pi over 3, which is 60 degrees, is 1/2. Cosine of 60 is 1/2. So cosine of 30 is the one that's square root of 3 over 2. Okay, so now let's see. We get some happy cancellations. Right? Secants are gone. Square root of 3's are gone. So we get square root of 3 comes out from 0 to pi over 6 of tangent square. How do we do this integral? How do we integrate tangent square? What's the technique?
You could change it to secant. You could do secant squared of theta minus 1, and then solve from there.
And then secant square is just tangent, and 1 is just theta, right? So we get square root of 3. So we turn it into secant square minus 1. So this becomes tangent minus theta. And then we plug in. Oops, it's pi over 6. Okay? If this was an indefinite integral instead of a definite integral, you need to understand that when you put theta here, when you go back to x, your theta, you have to use the inverse function. You either put inverse cosine or inverse secant, whichever the two you want, it doesn't matter. Okay? But just be consistent. But anyways, we have limits of integration, so there's no need to go back to x. So we get tangent of pi over 6 minus pi over 6 minus tangent of 0 minus 0. So tangent of 0 is equal to 0, and tangent of pi over 6 is square root of 3 over 3. So that becomes square root of 3 over 3 minus pi over 6, and distribute. So we get 3 over 3, so that's a 1 minus square root of 3 pi over 6. Okay, questions?
Yes, I have a question. I feel like you answered this question, and I was trying to figure out something else, so I didn't get the answer to this question. But how did you get pi over 6 and 0?
I just answered that question.
I know, because I had a feeling you were explaining while I was trying to figure
Let's see,
out the
how do you
question.
change the limits of integration when you're doing a definite integral? You go to your substitution. You go to your substitution and you replace the old variable with the old values and figure out what the new variable is.
So you inputted the 2 in tangent.
So first square root of 3. So we have cosine of theta equals square root of 3 over x. I use this one because it's easier for me to use that one than the second one. Okay. So I went here and instead of where you see x, I put square root of 3. Because x equals square root of 3. Yes? Just look at me, don't write it. Look at me so you can understand. Otherwise you don't understand. So this means that x is between square root of 3 and 2. So we just plug in this thing. When x is square root of 3, with square root of 3 here, we get that cosine equals 1. So the question is, what is the angle? The cosine of what equals 1? But if you want here, inverse cosine of 1. What's inverse cosine of 1? Put your calculator and it will tell you what it is. Tell you that it's 0. But just think about it. What cosine, the cosine of what gives you 1? That's 0. That's where the 0 came from. Then I do the same thing. When x is 2, I get square root of 3 over 2. So we're doing inverse cosine of square root of 3 over 2. And that is pi over 6. All right. Questions? Okay, so next class I'll do more examples because I wanted to do like 4 more, but as usual, you know. But next class I'll do more examples before we go to the next technique. There are more techniques. I mean, we haven't discussed how to integrate rational functions. Like if I give you this.
It's so sad because that looks so simple, but it's really not.
Let's make it more interesting.
Oh.
If I give you this, and then I could probably maybe do this. The point is that if I give you a rational function in general, we know how to do some of them, but many of them we don't know yet. Actually, something as simple as this. How do you integrate this?
You try. And then your tears wipe away the question, so then you don't have to do it.
So we do this by using a technique that you should have probably discussed in pre-calculus, but sometimes there's no time and you don't do it. It's called partial fraction decomposition. That's a pre-calculus technique. So we need to do this. We need to break this into partial fractions and then you integrate that very easily. Once you have it split into partial fractions, then it's easy to integrate. So basically, the way to deal with this is using partial fractions. So that's what we're gonna do in the next section. Okay? So I will assume that you don't know what partial fractions are, and then I will explain from scratch.